Hi everybody and welcome to the lecture on Systems Engineering Principles. My name is Biesbroek. I work at ESA in the Concurrent Design Facility. I started my career in French Guiana in 1997 and I've worked at several places at the European Space Agency centers in Germany and the Netherlands ever since. I've had my own company as well, where I focused on trajectory optimization software. And now, since 2010, I'm full-time staff member at ESA. I work on lunar rovers, as you see in the bottom, and also on the Clear Space One mission, which you see in the bottom right. When I'm not working, I like to do some car racing and mountain climbing. So this lecture is about systems engineering principles, and basically we'll be focusing on two things. First of all, the approach on system engineering, and secondly, the tools, and in particular the model-based systems engineering tools. Now, they're both very much connected. So once you start using an MBSE tool, so a model-based systems engineering tool, you're almost obliged to use a very systematic approach. And it's this philosophy behind it that I would like to show in this lecture. But first, why will we use MBSE and this design philosophy? Well, most of you, I think, will know the famous V model, where you start with a high-level design with high-level requirements, and you go more and more in detail, and then at some point you finish designing, and then you start working on building it and testing it first on the lower level specifications and testes, and then more and more higher on system level. Once you get to this place, how do you know if the requirements that you made are good, that you don't have conflicting requirements or overlapping requirements? And how do you know that the system is actually going to do what you designed it for? And this type of engineering with model-based system engineering is exactly what can help you with this in the design process. So what is it exactly? And let's focus on the modeling first. MBSE is really a technical approach to a system engineer. There's a shift in the focus from document-based design to domain models. So we try to move away from having the document as like the source of our design, but rather having a model as the source of our design. And MBSE can help you with this and can help you with design anything, be it a simple screen on which you watch television in a plane to a very sophisticated satellite. So it models your design in terms of requirements, in terms of functions, in terms of interface, the hardware, software, anything, you name it. But what is important is that if you start modeling, this model should be the true source of your design. Therefore, not the document. And that's also a bit what we'll focus on here. We looked at the model. Now, what is a system? Now, a system, if I use a fancy sentence, is an integrated set of elements which cooperate in an organized way to accomplish the design objective. What it comes down to is basically three things. There are elements, as you see, and elements is typically hardware. So this is what we call product tree. It could be a communication transponder or a solar panel, these kind of things. To cooperate in an organized way means we have a function tree. They need to fulfill certain functions. And that is another thing that we really need to model, and that is often a bit forgotten in terms of modeling in early phases. To accomplish a design, a defined objective means we need to have requirements. So for me, a system really comes down to having a product tree, having a function tree, and having requirements. So how can we start an MBSE design, so model-based system engineering design, in simple words? There are actually a few very simple steps that you can follow. And even if you don't use an MBSE tool, even if you design on a piece of paper, this method still applies. It's a very simple way, and maybe even a bit childish, but it really forces you to systematically think about important things. So what we need to do is define a CONOPS, which is short for Concept of Operations. From that, we're going to define what kind of functions are in whatever I'm designing, in my experiment or in my satellite. We need to understand what can influence our design, And once we know this, then we can already start looking into how can we define requirements, how can we link requirements to functions, how can we also identify hardware that could fulfill these functions. Here's an example for a concept of operations for an experiment in the ISS, the International Space Station. It's basically a list of phases, but they don't need to be in a specific order. They could be in any order in principle. They're shown here in order though. So first you would build and test your experiment. Then maybe you want to test your experiment. You need to test it in, for example, in our test facilities at the ESA Academy in Redu. But you need to transport it there. So there's the next phase is transport to Redu. Then you perform the test there. Then you need to get it to the launch site. So you transport it to the launch site. You launch it. Once it's in the International Space Station, you have to unpack it, install it, possibly in a rack, or install it wherever it needs to be installed. Then perform the experiment. And when you're done, you have to also get rid of it. So you have to unpack it, uninstall it, pack it up, return it to Earth, and maybe send it back to the user site. So you can see that even for an experiment, there's a long life cycle, and all of this can be modeled in what we call concept of operations. Does not necessarily need to be only during the time of running the experiment. It needs to really fulfill the entire life cycle of your experiment or your satellite. Here's another example, this time of a satellite mission that I worked on myself called ED Orbit. The mission objective was to capture a space debris, so a piece of garbage in space, and get rid of it by deorbiting it into the atmosphere. So again, I make my concept of operations. Sometimes in MBSE terms, it's also called use cases. How are we using our system? And some other tools called operational activities. Here I skipped a bit the design part, but I focus on the mission part. So first will be to launch it in space. Once we're in space, we do some testing in orbit. We call it LEOP, launch and early operations phase, commissioning of certain cameras maybe. Then we need to find the piece of garbage. So we have a transfer to the same orbit of where the space debris is. Maybe get very close, so what we call a rendezvous. And when we're very close, we can capture it. Once we capture it, then the next is the dispose of the debris. So here I have a whole set of use cases which define what we call the ConOps, the concept of operations. Let's look at what elements are acting on my system. In the middle, I have my space element. So this will be my satellite, my ED Orbit satellite. And in MBSE tools, they often use a kind of symbol that looks a bit like a little puppet to define what are actors. And actors are things that act on your design, be it good or be it bad. So one thing is the launcher, the launch element. The launcher will have an incredible influence on your satellite. It will shake it during the launch. It will put it in some orbit. The ground element as well. We are always interacting with ground stations on Earth, for example. There's the environment, the space environment. And in this case, because we're also going to go into the atmosphere, there's also the Earth environment that will have an influence on our system. And there's the debris element. For example, once I touch the debris, the entire moments of inertia of my system will change. And the system needs to be able to react on this. Now, like I mentioned here, I've only shown the actors and the ConOps for the actual space mission. But you could think of more things. There are types of actors that have an impact as well. For example, there are stakeholders, maybe scientists, if you have a scientific experiment or a scientific space mission, or the European Union, or could be anything. The same for test facilities. If you want your experiment to be tested, you have to make sure that it fits in the test facilities, for example. It needs to be mounted, etc. So there will be requirements coming from your test facilities towards your system. So that test facility is an actor on your system. The same with transportation. If you want to transport it in a truck, how are you going to mount it in a truck? For satellite, for example, we need maybe mounting brackets, we need to hang it up maybe, or transport it by ship or by plane. It needs to be in a certain box, etc. So there could be all kinds of actors that you can think about. Now let's put this together. So I've shown here on the left the list of actors: launcher, ground, debris, and environment. And I've shown in the middle the use cases, so the ConOps. Now we can think a bit more in depth. What activities am I performing for each use case in the ConOps? So if I look into launch into space, actually I'm not doing much. I'm just staying alive. My satellite is typically just trying to survive the launch. And the only thing that is acting on the spacecraft at that time is the launcher. But once I get into orbit, so when I go to the second use case, for example, perform LEOP and commissioning, I'm still staying alive, but my environment now is different. I now have the space environment acting on my spacecraft. Also, I'll be communicating to ground, sending housekeeping telemetry back to ground. So therefore, the other actor linked to this use case is ground. And I can continue doing this and defining activities for all the different use cases. For example, when I get close to the space debris, the rendezvous with the debris, I need to precisely locate the target. So I need to know the position of the target, the debris. So the debris is an actor. The environment will still be an actor, and I will still be communicating with ground. So ground will also be an actor. When I capture debris, I have to capture it. When I dispose debris, I have to lower the orbit. I have to make sure that the debris re-enters over an inhabited area in case anything falls down. So these are all activities, and in principle, these are functions that the spacecraft, that the system therefore needs to do. And this is a very simple way of systematically deriving functions for each use case in our mission. So this is a functional diagram of our actual ED orbit design that we've done in this case with company Airbus. You can see on the screen several functions that I mentioned before, like operate mechanisms, have thermal control, provide operations, these kind of things. And also there are functions in this case for on-ground segment and for launch segment. And in the MBSE tool with which this is made, if you click on this, then there will be a hierarchy and have more functions, let's say mini functions under the larger functions. Here's another example of, again, the same mission, the ED orbit mission. This was from a design by a company OSB, where they defined in MBSE tool all the segments of the ground segment and all the functions there. So you see in the middle ground system and 1.1, the first function is to transmit telecommands to the spacecraft. And you have other functions like perform ranging or receive telemetry and these kind of things. You also see other segments. You see the spacecraft. On the left, you see the spacecraft operator. On the right, you can just see ground stations. So they are at possibly different places, and you see lines interconnecting them. These are interfaces, of course. And one nice thing also about MBSE is when you define an interface, which is simply drawing a line between one functional block and the other one, you can indicate what format that interface needs to be. For example, we can indicate what kind of format the housekeeping data needs to be sent to Earth, or what kind of format a telecommand needs to be sent to a spacecraft. And in fact, with the mission that I'm working for now, ClearSpace 1, we are directly linking ground segment software directly to the MBSE tools. And the software for the ground segment is, for example, sending the telecommands to the spacecraft, and it will get its format from the MBSE tool, which is another indicator that the MBSE tool is the one source for your design. Finally, this is the final example for ED orbit. There are other things you can do with model-based system engineering, and one thing is to create sequences of events. So you have a sequence diagram, as they call it. In this case, here's an example of what happens once you've captured the debris. Once you capture the debris, you need to stabilize the whole stack of the spacecraft and the debris. And that can involve several things. It could involve an operator, for example, who could send telecommands. But as you see here on the screen, the operator, which is on the top left, has no event at all. So that means that this entire sequence is completely automated on board the spacecraft. You see in the middle what the system is doing. The system in this case being the orbit satellite. Like it is in a capture mode, so this onboard computer switches to a capture mode. Then it needs to get its position with respect to the target, which is the debris, and possibly move a little bit. And in order to do that, it needs information from the target. It needs to have its position. So on the right, you see the target satellite. In principle, this is a dead spacecraft. This is a piece of garbage. Nevertheless, in terms of modeling, we create that an event that it has its own moments of inertia, for example, its own position, and that position will be given to our spacecraft, whereas in reality, the spacecraft will measure it. But this is a way of modeling, let's say, several events that happen in chronological order. And another thing the MBSE tool can do for you is to simulate this. It can actually run this scenario. It can run this sequence of events. It can insert with the kind of Monte Carlo analysis parameters, such as, like I mentioned, the position of the spacecraft, the relative position of the debris with respect to our ED orbit spacecraft. Therefore, choose certain values within a range and run the sequence of events. And it can mimic, for example, how the onboard computer is sending telecommands to the AOCS system to fire thrusters here and there, these kind of things. You can make it as complicated as you like. Coming back to then our functional diagrams. Now we are in a position to create more requirements, maybe not just functional requirements, but also other requirements. Again, when we know that we are staying alive during a launch, we can easily create requirements on, for example, coming from the actors, in this case the launcher. We know that the launcher will shake it, so there will be frequencies. These are all in user manuals. We can get them. We know that we will have to fit in the fairing of the launcher, so there's a maximum volume, which will be a requirement. There's a maximum mass that the launcher can bring up, so there's a mass requirement. Maybe we need to survive on our own battery for half an hour, so there will be a requirement on the battery there. And I can go on and on like this. For example, if I communicate to ground, what kind of frequencies? So there will be requirements on which kind of frequencies. There will be requirements on the maximum time in which I can download any housekeeping data or any other telemetry. When I locate the target, how sensitive do my sensors need to be? How can I make sure that the camera or the onboard computer can distinguish between a star and the space debris? So it will be very easy in this way to create a whole list of requirements, not just functional requirements, but any other requirements coming from just the situation or from the actors. So another message that I would like to give is, it's easy to design a good system. You just have to design a system that shall do what it's supposed to do. But what I would really like is you design a really good system, which should also do well when there are failures, and especially, when you do experiments or when we are in space doing experiments, there are bound to be failures. There are bound to be things that go wrong, even in the most sophisticated projects like the Apollo missions. Apollo 11, it overshot its landing site, and still they managed to land it. Apollo 13 is a unique example where everything went wrong, and they still managed to get the astronauts back to Earth. But there are, even on smaller projects, we could easily have an AOCS failure, so an attitude failure, and have one side facing the sun for a long time. What do you do then? So we have to come back to the requirements. So we know that when we have bad requirements, we are doomed for sure. But when we have good requirements, that still doesn't mean that we have a very good design. If I take an example, that we make a Mars lander and we design it such that it has sufficient clearance to land, even if there are rocks up to 30 centimeters. And then in the end, we launched the satellite, we landed on Mars, and it lands right on a rock with 60 centimeters diameter. So clearly we did not design for this, but still there are always solutions to still recover part of it. If you have, for example, if the space is tilted because of this rock, and we only have one ramp to egress a rover, we may be in trouble. But if we have two ramps, we might be able to egress on the other side. So that is one way to think ahead on possible problems and try to already solve them. And this we call feared events. And when we start modeling requirements, it would be best that from the moment you start designing, you also start defining requirements linked to feared events. So on the right, I give some examples. What if the battery runs out before deploying the solar panels? What if we have no ground station contact within an hour? We have to search for the spacecraft, for example. What if we are getting close to the debris that we want to capture, and the only time that we can capture is when there's no sunlight, when we are in eclipse? So would it be good then to have just, for example, a visual-based camera, or do we need to add maybe also an infrared camera, or do we need to understand a way that we can capture it later to be always in sunlight, which may cost more propellant? So these are things that we can think about and already start to find solutions for. With these kind of things, it's good to find people who are very, very negative in their minds. If you tell somebody, I'm going on holiday by car, and they think that you can easily crash, or the flat tire, or you may be late, these are the perfect people to come and give you a list and help you with these kind of feared events. It will be good to really think in a negative way, so, which is difficult when you design, because you're very positive about your design, you're very optimistic. Still, it will be good to think what can go wrong for each function and for each use case in the ConOps. Again, it needs to be following a very systematic way. So how do we model all of this? Well, in the past, these three elements, the product tree, the function tree, and the requirements, were often modeled in different tools. So for product tree, we would have Excel for Microsoft or any CAD file, and in the worst case, documents. And the same for function trees, we would have documents or possibly some simulators. Requirements were often a bit better modeled. We have specialized tools for requirements, such as doors, and otherwise Excel, or again, in the worst case, documents. Now, MBSE is really taking over, and in particularly on the function tree and the requirements, they're often modeled together in MBSE tool. That doesn't mean that we cannot get documents or simulators or Excel outputs. Typically, these MBSE tools can easily export any function list or requirements list to Excel or to a document. And often we can also link simulators or other software to MBSE tools. When it comes to the product tree, it is often still done a bit separate. We have very specialized tools such as Comet or other CAD tools to work on the product tree. What we're working on, of course, is that everything can be modeled into one MBSE tool. We're not there yet, but certainly some tools are being linked together, and some are even being merged together. When I look a bit ahead, possibly we would like to make things more, let's say, visual, where, for example, I see on the right here my ED orbit satellite capturing a very large satellite in a simulation. And if I would click, for example, on the robot arm of the ED orbit, I could easily get any parameter that is of importance in the product tree, such as the dimensions or the mass, the identification number, and these kind of things. Or I could ask what kind of requirements are acting on this robot arm, what kind of requirements are linked to this robot arm. And later on, when we start building spatial, we can continue using these tools, and for example, any test report could be linked in the MBSE tool and therefore easily seen and found. In the future, we will also see that integration could even be led, let's say, by MBSE tools. And We're investigating the use of virtual reality in this kind of world. It is now a bit unclear if it brings an advantage, but of course it's a very interesting environment to be working in. So this is for reference. I list a small subset of the many MBSE tools that we often use, not just at ESA, but of course our partners in industry as well. Capella is an open source tool, and I've shown the links where you can find these tools. There are other tools, there are online tools like InnoSlate, and tools where you probably need to purchase a license like Genesis. No matter what tool you use, they all have a steep learning curve. So as a warning, it will take quite a bit to get to learn these tools and these methods well. Nevertheless, once you know it and you keep using it throughout the project, it will certainly have an enormous benefit, and it will certainly save a lot of time and a lot of errors, in particularly later on in the project. When it comes to the product tree, like I mentioned before, at the moment we still have specialized dedicated tools for product trees. These are also part of model-based systems engineering tools. One is Comet, which is a tool that we endorse from ESA very much. It is used a lot in the Concurrent Design Facility at ESA, for example. Another tool is Valley Space, which is an online tool and also allows for implementing certain formulas into requirements or formulas into the product tree. So some I mentioned, some I didn't, just to highlight some other advantages that MBSE tools have. It can check automatically if certain functions are linked to a requirement or not. And if there are no requirements, for example, linked to a function, that means that something is wrong. So it can highlight these errors automatically for you with just one button press. It can also sense if there are overlapping requirements on one function, for example, or if requirements are not linked to any function, or if requirements have no hierarchy, for example. Another advantage is that it can automatically generate reports for you. These are getting more and more sophisticated, so it's not just a list of the product tree. It can even have automatic text generation and automatic figures generation and these kind of things. There are other automatic procedures in MBSE tools, a bit like the autocorrect functions on mobile phones. When you start typing in something, it can already almost finish your sentence sometimes. And MBSE tools can do the same. Once you start typing a certain product, it can sometimes tell that there will be other product linked to it and automatically do this for you. Like I mentioned with the events diagram, MBSE can run simulations for you, which could be, let's say, a first high-level check if what you're modeling will actually work when you start running it. And finally, MBSE can define units for interfaces and therefore avoid the wrong use of units. I mentioned the interfaces before. You can define the format of an interface, but you can, for example, say this interface has to go via RS422, or anything going through this interface has to be with the unit watts, and therefore you avoid that people are typing 3 kilowatts instead of 3 watts. So finally, I have a few messages that I really like you to take home. Like I mentioned, it takes time learning model-based system engineering. The philosophy behind it is fairly simple, but once you start modeling it, it can take some time to learn, but it does really pay off in the long term. No matter what you do, which tool you use or how you use it, at least follow this systematic way of working when you get to when you start from scratch. Once you have the mission objective, define the concept of operations, define the functions, and from then you can define the requirements and the products. You should have one true source of your design. Try to avoid just referring to documents and changing numbers in documents and have a new version number, whereas in the model it has an old value. That should not be the case. The model should be the one that is the most up to date. Identify feared events as soon as possible. So I know it sounds negative, but from the moment you start thinking about your design, you should also think about what could go wrong with your design. Finally, choose an MBSE tool before you start the design and stick with it. Again, it's very difficult to learn a tool, so if you start changing tool during your experiment project, that will only cost a lot of time. So choose it right from the beginning and stick with it. So I hope you enjoyed it. Good luck with your design.